Okay, so we continue with similar topics. So still we try to generate randomness. And the next talk is given by Prashanth. He is from Technische University of Dresden. He will talk about redesigning physical layer secret key generation for post-Shannon communication.
Hello, everyone. Thank you very much for inviting me here, and welcome to my presentation. I'm Prashant. I'm working at TU Dresden as a researcher, and today I would like to talk about common randomness generation, and the topic of my talk is on redesigning physical layer security generation. The idea is that we are trying to redesign PLS key schemes or physical layer security schemes, and so we first, of course, begin with the motivation. Why is it that this is an interesting research for me? So this comes as part of the common randomness generation, and then we take a look at the fundamentals of generating common randomness, and then we take a look at a particular problem statement that I'm interested in. And then we provide solution in a two-part system. Part one is on correlated observation. Part two is on improving the common randomness rate. And then we go for the conclusion and future research questions. So, of course, so let's begin. So as the name suggests, common randomness means we are generating a random variable at two or more intended terminals, and it's visible only to those two intended terminals. Um, Conveniently, common randomness has significant use cases in identification codes, which improves scalability. And it can also be used in robustifying system against jamming attacks. This was paper proposed by Professor Booker. And common randomness is also used in providing information theoretic security, which comes under physical asymmetric key generation. So there is use case in improving scalability, security of future communication networks. So it's a very interesting research for me. So let me give a brief illustration on how the application looks like. So first, let's take a look at a classic example of Shannon's way of communication. Here we have replication of bits from A to B and or from B to A. Yeah, so we have a replication of bits from A to B, and in Shannon's way of communication, we just replicate the bits, and we are more concerned about the transportation, not on the semantics of the communication. However, when we talk about identification codes, so we are more interested in whether for example, whether the message is intended for the receiver or not. So we can instead of replicating the bits from A to B, we send a minimum information, and this can contain like a code word and the position of and the randomly selected code word and the position of the code word. And through this, we can actually compare to say the Shannon approach. We can actually reduce the bottleneck at the receiver side. But then again, we have to transmit the randomly selected position. But then when we use common randomness, then we do not have to transmit this position, this randomly selected position. We just have to transmit the code word. So this actually reduces the bottleneck. So this is one illustration of how we can use common randomness for ID code words. And then we also have this use case of robustifying your system against jamming attacks. So if you use common randomness, then you can actually robustify your system. And then there is this classical use case of encrypting a message so that the eavesdropper is not able to decrypt. So we can make use of common randomness here so that the messages do not get leaked when you perform over the air transmission. But then the question is, why can't I just use a software-based random number generator or software-based common randomness, which we call as pseudo randomness here? The issue is that pseudo common randomness in case of physical asymmetric key generation offers certain level of computation security, but then if the eavesdropper has the decoding knowledge, then they will always be able to replicate the pseudo random number generator, because it has this property that you will always get the same random sequence if the seed to the algorithm is same. And then there's also the issue of periodicity. So if we have a pseudo-random number generator with same seed, then after certain repetition or after certain duration of time, the sequence starts repeating itself. Uh, and then there's also the issue that the randomized protocols are faster than deterministic protocols. So there is clear indications that common randomness can be used, and it's actually quite necessary if you are really concerned about the security part as well. So now that we did take a look at some brief illustration on where is it that it's useful, and did take a look at the motivation. So let me give a brief explanation on how common randomness is generated. This was mainly from Alsweder's paper. Uh, so we have two terminals which are observing a common source. Terminal A is observing xn and terminal B is observing yn. Um, so terminal A can now generate a random variable based on its observation of the common source, and terminal B can also generate its own version of randomness, but it will be quite erroneous because the observation of the common source is not perfectly correlated. So there will always be some errors in the way the common source is being observed. And in order to reduce these errors, we assume a notchless channel that is established between a unidirectional notchless channel that is established between terminal A to B. And then the terminal B can use this information that is being sent to align its random variable with respect to the random variable generated at terminal A. Of course. So if the correlation is perfect, then we do not have to transmit any of this information on the notchless channel. But when it comes to physical ASIC key generation, there will be some errors. We will discuss that part later. So what we are more interested right now is on generating common randomness for wireless communication. And this procedure has already been done as part of physical ASIC key generation, where the channel reciprocity between the legitimate terminals are actually used in as a common source of observation. So we observe this reciprocal channel properties, and then we extract random bits out of it. And this was mainly used in PLSK schemes. Um, but then when we talk about identification, where it's a more of a goal-oriented communication aspect, so we require secure identification, and we also require information theoretic security. And the idea is that the PLSK schemes on their own actually generate common randomness at a very low rate because their primary objective is to provide security. And so for identification, replicating the PLSK schemes and using it for common randomness generation is not a suitable idea, particularly if you are interested in identifying very large set of messages. So the idea is that we want to generate common randomness at much faster rate. And that is the problem statement that I'm trying to address. So first, we take a look at the basics of PLSK. So we have 5-step process for physical ASIC key generation. The first is channel probing, where the legitimate parties send pilot signals to each other, and it has to be done within a certain duration of time to read reciprocal channel properties. And then you try to extract channel properties from the received signals, that they received pilot signals, and then you quantize it. And then you perform reconciliation by sending this minimum function that is required for the terminal B, or like the terminal on the other side, to align its random variable to the one on terminal A. And then in PLSK schemes, they use privacy amplification because this information, which was yeah, okay. This information, which was leaked here, that can actually potentially cause a leakage of information, and we do not. And in order to prevent this leakage of information, they use privacy amplification, so that the privacy amplification normally contains functions like a deterministic hash, where they make use of avalanche effect to reduce the information leakage. So we try to address the issue that we try to improve the common randomness rate compared to the PLSK schemes in a two-part step. One is by improving in the first two stages, which we call as the part one, which we term as part one, which is by improving the way we observe the common source. And then in the part two, we try to improve the common randomness rate by improving the functions that the way we try to extract random variable out of it. So let's get into each of the parts. So first, part one. So this was a testbed that we built. The testbed consists of two SDRs. It consists of two SDRs. This is terminal A and terminal B. And we have one host machine which provides slot synchronization, and we perform communication through the host machine. And then we have the LAN switch to perform routing between the SDRs. So this is the basic setup that we have built in our lab. And following are the key metrics that we'll be evaluating. So these are the key metrics that were used even for the PLSK schemes. So we just try to take a look into it. So we already described the importance of the correlation. So if you have high correlation and sufficient entropy, then you do not actually need to transmit this minimum information. So the correlation plays a very important role in extracting random variables. And then here we try to take a look at these four key properties of received signals to observe common source. So the first is frequency offset of the carrier frequency, and then we take a look at the received signal power, and then afterwards the amplitude of the received signal, and then we take a look at the phase offset at the SDR terminals. And then we also take a look at the bit discrepancies. So higher the bit discrepancy means that we need to send more information on the noiseless channel to correct these errors, which would have been used for transmitting more useful information. So higher bit discrepancy is not a desirable option. So we want to reduce the bit discrepancy more. We want to increase the correlation. We want to reduce the bit discrepancy more. And then the NIST test result was used by several PLSK literature where they evaluated the randomness of the generated random variable. So the results, so we evaluated using two different channels. One was static and another one was fading channel. And we noticed that when you introduce fading channel, you actually introduce entropy. You notice that the RSI and the amplitude, the received signal power and the received signal amplitude displayed some correlation and also displayed some entropy. And compared to static channel where there was no indicator of entropy being displayed. However, the frequency offset had good correlation, so we wanted to retain the frequency offset. And the reason was because higher the correlation means you achieve lower bit discrepancies. So that means that you can generate randomness at a much lesser number of reconciliation bits. And we performed, what we did was we extracted some RSI information and CFO frequency offset information, and then we tried to quantize it by using 1-bit quantization. We used a mean or median of the set of observations, and any value higher than the mean or median is quantized to bit 1, or any value lower than the mean was quantized to bit 0. And by performing this, we calculated the bit discrepancy, and we noticed that higher the correlation, lower the bit discrepancy. So, and then we did the basic PLSK part where we tried to extract randomness out of the quantized bits. What we did notice was that PLSK scheme had this privacy amplification where they extracted, where they observed n bits and then they extracted r bits out of it, where n is greater than r. And this was quite lossy by itself. So this was, there was a lot of loss of bits over there. And we wanted to see if we can do better. So this was already used in several PLSK schemes. So we were more interested in knowing whether we can do better than this. So now we go to the part 2 where we modify the function how we generate the common randomness. So in part two, so we have to again take a look at the basics, the fundamentals. What we already know so far is that the identification capacity is lower bounded by common randomness capacity. So we need to take a look at how we can generate common randomness at faster rate by modifying the functions. What was already tried by several PLSK schemes was to improve the bit generation rate by increasing the order of quantization. But the problem was that if you increase the order of quantization, then you increase the bit discrepancies and you need to transmit more amount of information here. So this incurs very high reconciliation cost, which could have been actually used in transmitting more useful information. So what are the source of these errors? So we have imperfect signal processing, which could be because of the timing synchronization errors or software errors, some signal processing errors. And then there would be internal noise or hardware errors, which are highly uncorrelated between the terminals. And then there is channel probing errors because we're using half duplexing mode in our hardwares, in our PLC schemes, and that could actually provide us non-simultaneous channel measurements. And then there was also random noise that were introduced by quantization. We'll come to that part soon. Then the question is, can we correct these errors? So what we did was we wanted to take a deeper look into how this can be corrected. So assume that you have a random variable and that you want to convert it into bits. And when you do that, so normally what we do is like imagine like a building and you're mapping the random variable. And each floor represent bits, which can be mapped into the random variable. And the idea is that if the mapped random variable lies in the same floor, then you get the same bits. Because of the errors that I already described earlier, these mapping can actually then the random variable won't be mapped to the same floors, and because of that you actually get bit errors. And because of the existence of the floor difference, you always end up with the bit difference. So how can we deal with that? So we have to remove highly uncorrelated parts in the random variables that we're generating, and we have to retain the correlated parts. And we noticed that the highly uncorrelated part was because of the mainly belong to the upper frequency part, and so we had to filter out the signal. So we filtered the signal at both the random variable, and then we performed the same plotting of the bits, and we noticed that the floor differences considerably reduced when we tried to plot, and this was a good sign. But however, we noticed that the subsequent plots contain very high bit discrepancies. We noticed that even if there is just one floor differences, there was very large number of bit discrepancies because of the nonlinear representation of bits. So what we did was we just used gray codes. Of course, this was already published in several state-of-the-art PLSK schemes, so we just employed those, and we used gray codes to make sure that the adjacent floors only have 1 bit differences. So this is how the modified PLSK scheme looks like. We have 2 stages of noise reduction. One is here in the filters where we apply the stage 1 filters, and on the second stage we apply the gray code encoding. But then the question is, which filter should we use? So in order to determine which is the best filter to use, we have to determine what improves the common randomness rate. So, and for that we have to define what common randomness rate means. As the name implies, common randomness rate means rate at which you are generating commonness and randomness in the random variable that you're generating. So it has to contain both these properties. So we have for an illustration we have 3 examples. In the first example, we are generating a common random variable which has very high entropy and very low bit discrepancies. So this means it's high commonness and very high randomness as well. So we achieve very high common randomness rate of 2 bits per observation. And the common randomness capacity is 3 bits per observation because it's the entropy of the observation, and we assume here that we have very high entropy in the observation that we are observing, or in the channel observations. On the second part, we have common random variable which has low entropy and but also very low bit discrepancy. So that's a indicator that the entropy is low. So that's why the common randomness rate reduces. And on the third part, we have very high entropy, but also very high bit discrepancy. So that also reduces the common randomness rate. So this part is before the reconciliation stage. So we are not considering the effect of reconciliation because we also have to consider that we are not transmitting too much redundant information to correct the bit error. So we had to consider the size of the reconciliation, that is, which is directly indicated by the bit discrepancies. So the results is that we already know some of the key metrics that is already used in PLSK schemes, but we are not interested in that. We are more interested for identification. So we evaluated the common randomness generation scheme using these two factors, which is the common randomness rate and the common randomness capacity. According to some of the key state of the art, which is the using discrete cosine transformation and wavelet transformation, we replicated the same work in our test bed, and we noticed that the PLSK schemes that they were using, the common randomness rate was quite low compared to using filters with very high cutoff frequency. And that is what we observed here. So all the beginning 3 filters, they displayed very high common randomness rate because they had very high cutoff frequency. They had very low cutoff frequency. Sorry about that. Yeah, so and then the common randomness capacity was quite constant. For 1024 observation, it had 10 bits per observation, so this remained constant. So we were able to achieve very high common randomness rate with very low cutoff frequency for the filters. The state of the art, the same filters which are already used in state of the art were contained very high cutoff frequency, and that's why their common randomness rate was quite low. We just had to modify the filters a little bit. And then the trade-off that we need to consider when we were designing the common randomness scheme was the length versus the cost. So if we wanted very large length common randomness, then we had to sacrifice by introducing higher reconciliation cost. So this was the trade-off that needs to be considered when we are designing the system. And this is the result that we obtained. So on the x-axis, we increased the order of quantization, and we noticed that for the increased order of quantization, higher reconciliation cost had to be paid here. And here we had to sacrifice lot of time in order to generate the same size common randomness. So we got some random variable out of it. So now the question is, how do I test whether it's truly random or not? Now we go back to the same design, the common randomness generation scheme. And then when we plotted the random variable, we noticed several, because of the presence of filters, there were several these low frequency characteristics in the random variable. So there was this flat here, and then there's flat here, flat here. So this displayed very low frequency behavior, and this was mainly because of the filters, because we use such low cutoff frequency in the filter. So we had to introduce a randomization agent, but we couldn't use the same privacy amplification scheme that was used in PLSK. So we had to introduce randomization scheme, which did not cause issues, which did not incur loss of bits. So what we did was we used a random shuffling algorithm where we made use of a pseudo random number generator to shuffle the index of the generated random variable before shuffling. So, and then when we plotted the random variable, we noticed several high frequency characteristics. So several high frequency characteristics. So, and then when we tried to plot the DFT frequency spectrum, we noticed that the energy was more concentrated on the low frequency part before randomization, and after shuffling, the frequency distribution was much more uniform. Um, and as a reference, we also plotted the frequency distribution using deterministic hash algorithm or deterministic hash function. And as a reference, you can notice here that pretty much the frequency distribution of the hash and the shuffling was pretty much the same. So that's good news. So compared to the PLSK schemes, which I described in part one, now we were able to generate more number of bits for the same set of observation. So that's a good news. And we were also able to pass several NIST statistical tests. So the PLSK already were able to pass several NIST statistical tests, and now we are able to pass as well. And then we were able to generate a higher number of bits for the same set of observations. So this is a good news. But what about the cumulative? So what does it mean overall? So the cumulative results compared to several state of the art, we analyzed the bit discrepancy or the parity bytes that we needed to transmit to correct the errors. And we also analyzed the number of observations that we needed. And we noticed that the PLSK schemes, which was several PLSK schemes from here to here, they either require higher number of observation, which means more time is needed in generating the same set of common randomness for same size common randomness, or they incur higher reconciliation cost. That is, they needed higher bits to correct the errors at the terminals. Um, our scheme, on the other hand, because we used the filters and higher quantization order, it reflected much closer to the ideal state where we needed lesser number of observation and lesser number of reconciliation cost. So this is a good news. So this is something good. So then to conclude, were we able to generate common randomness at a much faster rate at lower reconciliation cost? So answer is yes. Uh, so for that, we need to take a look at the reciprocity. We need to observe a random variable which is highly correlated. That's what we did, and we used the most highly correlated variable as a common source of observation. And then we introduced multi-bit quantization, and random shuffling. This was the unique part in our work. And then we try to take a look at the associated trade-off. We noticed that our scheme provided a really nice balance to the time and the cost. And we had up to NC minus R bits of improvement compared to the PLSK schemes. And we also were able to generate it at much lower reconciliation cost. So this is improvement that we were able to make with common randomness generation. For the future research, what we discussed so far is mainly information theoretic approach. We were not that focused on the temporal common randomness rate, but on its own, the temporal common randomness rate of the test bed that we developed was quite low. So, and then when we talk about improving common randomness, we can also improve it by integrating with multi-carrier systems such as MIMO, OFDM, and channel impulse response, for example. These could actually be used for analyzing as a common source of observation. And then integration with identification codes can also be done. But then the question is, we already have a merchant twist algorithm, which has really good periodicity for a software-based random number generator. And then we are trying to also analyze what is the issue and what it is that we could do here that makes it distinct from Merson-Tusti algorithm. So these are some of the state-of-the-art references that we used. And thank you very much for listening to my talk. And yeah, I'm free to questions.
Yes, thanks a lot for the talk. Are there questions or comments?
Thank you for the interesting presentation. I've seen that in the first step of your sequence, you have this channel probing, right? So you extract these CFO parameters, RSSI. Okay. So in some way, all this relies on the fact that you own some characteristics of the hardware that you are using, right? So, for example, CFO, you could reduce it with the better hardware or make it worse. So how do you think this could impact your solution? And another question is related to, since you are addressing wireless system, related to mobility. I understood that your test bed was a fixed system, right? How do you think this could work in a mobile wireless communication?
Yeah, so the idea is that whatever you're observing for common randomness generation, it has to be highly correlated and it should display certain entropy properties. So as long as we maintain this, we should be able to generate common randomness, irrespective of what we're observing. If the signal processing is better, and if you're getting highly correlated signal measurements at both of the hardwares, then that's really good. That's good news, and we can actually generate at much faster rate, provided there's entropy there.
But let's say that you have uncertainty about the quality of the hardware that you have. You don't know exactly how good is the hardware. Then would that be an issue?
I mean, if the way the signal processing is done in the hardware is not good, then of course that adds a certain level of uncertainty there. Again, this is of course the hardware dependent approach. The hardware independent approach, the entire steps that I described for the common randomness generation, that is still hardware independent approach. The result that was displayed is with the USRPs. In case the signal processing is wrong or if the hardware is not good, then that's a separate research that it's research specific to that specific hardware or that specific system, for example. So it's a case-by-case basis. But here I'm more interested in giving a hardware independent, software independent approach. Could it could it disrupt the common randomness generation? It could. But then again, it's a case-by-case basis. So for that particular hardware, for this particular system, so what was the result that I obtained? So could it be made better? So that's a case-by-case basis. So we have to investigate it likewise. For the fading part, for the movement part, on the left side, we introduced, so here, we introduced certain movement here. And here, this is static channel. So here, just we did nothing here. So we just kept the hardware and then we ran the program, and nobody was in the lab, and that's how I got this result. And here, this result was mainly by moving one of the hardware from left to right at random instance of time, and we noticed the observation, the channel observations here. So with movement, we actually achieve higher entropy and higher correlation. So that's a good news. Of course, this mainly for the static part.
Okay, thank you.